We just got our bunch of contingents coming in.
We have people. Yeah.
We have people, and so a quick announcement on the Eastern Conference. We we accidentally sent off the wrong pay schedule for the Eastern Conference, and here's the new one. We sent this off to the mailing list. So if you don't realize, the Eastern Conference is in Green Bank from 4 to 7 August. Okay, and the prices are a little higher than was put in the journal. So what do we got? We got the $275 if received by July 1st. Includes meal but not lodging. And if you have a guest that's not participating in the conference, that's only $75 for the guest. After July 1st, non-members are $295, and let's see, and the rest of that stuff there. Yeah, walk-in registrations are $350 if space is available. All that's for food and everything like that. So the real price is the food and the various other costs doing the conference. So it's a little. I think it's up $25 from last year, but Jay's had this all worked out, and we got all the permissions. It's going to be a pretty good conference. We are looking for a couple more papers. So anybody that wants to do a paper, talk to Jay, or if you send it to me, I'll forward it to him. Let's see what else. That's about it. Let's see. Ted, you got anything going on?
No, I keep working on projects and hitting interference, so I'll keep working on that. Ezra keeps getting dinking along, and I gotta finally post something. Otherwise, I have my list of projects gets longer. Nothing to report.
Okay. Skip.
Yeah. Do I have anything? I guess I did find out that the 40-foot is Sue Ann's going to be deciding that, figuring that out, according to Mark Barnes. So,
what does that mean? The 40-foot,
well, the use of the 40-foot has been, kind of in question each time. I guess each year we wonder whether or not, for sure that there isn't going to be a large group or something like that. And Mark said that when I entered my when I did my room reservation, et cetera, that they were informed about the 40-foot requirement. I mean, it supposedly was disseminated to the education public outreach. And
so this is for the conference.
Yeah, for the conference, right. Oh, I'm wondering if that's what when you called on me, if you were asking me for any updates on the conference.
Well, that too, and any projects you're currently working on.
Oh, sure, yeah. Well, I'm working on this interferometer. I got this paper that was submitted, and I guess I think I mentioned last time that it got into the popular physics category in archive. I was kind of blown away with that. That's someone I looked up the names of the moderators for archive, and I thought that they'd be like grad students at Cornell, but they're people from like university professors and deans. I mean, not deans, but like heads of departments. They're very prestigious astronomers, physicists, electrical engineers. I mean, they got to be like professors, or practically, it seems like. There might be some grad students in there, but they're from all over the world. In fact, it seemed to me that most of the archive moderators are outside the United States. So does anybody want to see a short presentation? I'm preparing for the New Hampshire Astronomical Society.
Go ahead.
Okay, so I'm gonna share screen here. Hopefully everything will work. Let me see. I might. Why don't you let me get things started? Because I gotta bring up some things, and you can
Okay.
come back to me. Yeah.
All right. Ed Harfman.
Well, Friday I retired mostly. And so now I get a little bit of catch up on some sleep and get my brain back into at least one hemisphere and actually get started, trying to get my dish up and running. And this is just the little scope in a box guy. I've never gotten him actually working. Get him working and, start learning and doing the stuff that I've wanted to for almost a decade now. So looking forward to that.
All right. And you can always use your time machine, the TARDIS back there to help you with your time management.
Well, the rotor is stuck, so it's got some problems there. I need to figure out what to do with it.
Oh, okay. Preston.
Okay, I really don't have anything this time, and so interesting to hear what everyone else has.
Okay. Helen.
Oh, good morning. Yeah, I'm getting myself together. The coyotes were really out big time last night, and there wasn't even a moon. Maybe they got excited over the meteor shower. But I wanted to thank you for counseling me to watch the your TV station on YouTube. That has fascinating information, and so I've been learning and really enjoying it. And I have a couple of friends that are joining me, so I just wanted to say thank you.
All right. And we'll get you into the 21st century by not saying TV station on YouTube. All right.
Oh, okay.
You're gonna be
Okay.
an official streamer. We're
Oh, my.
streamers.
Oh, I don't know
And
if I can handle all that, but I'll try.
I know. We're influencers and streamers, I think is the official terminology from the kids. At least that's what my 9-year-old grandson says.
Oh,
Okay.
All right. Thank you.
See ya. Skip, how you doing? Ready to go?
Yeah, I think I can share screen. Let's see if it works. Let's see. I think I'm gonna bring up this one. Share. Okay, did that work?
Yep.
Okay, I'm gonna play slideshow. Yeah, so this is do you see a search for extraterrestrial intelligence project?
We do.
Okay, so yeah, I'm giving this talk on Friday. It's I'll just go through it real quick, but so the paper that I was talking about is on an interferometer. So this is the 5th paper that I've given on this strange location in the direction of Rigel, the star, and I'm this is a really short. This is only like 5 slides, 6 slides. It's just a short presentation for the New Hampshire Astronomical Society. But I've explained that things. This is part of my presentations that I gave like last year. Is that we used the 2 telescopes, the one in Green Bank, 40-foot, and we used the Haswell dish, 60-foot. And what I look for are pulses that are close together in frequency. And in this case, in this experiment, I'm looking for anything closer than 100 kilohertz. So 2 tones that are closer than 100 kilohertz from each other. And And in the previous things, we were looking at all sorts of simultaneous pulses that were showing up on both telescopes. And then those are the papers, those 4 papers at the bottom are the 4 archive papers that describe that work. And so it turns out that it has this strange thing that we observed back in 2018 and 2019, where that one direction near the star Rigel at minus 7.6 declination had these anomalous pulses that were showing up on both telescopes at the same time on the same frequency, which led to me just continuing to look in that direction. But the way I determine whether or not there's something significant is by looking over a range of declination of right ascensions to basically use the sky as a filter. So, and the location of that star is like right above Rigel, where those strange pulses are coming from. And my brother made this. I think I showed this last year at the conference. This is a fella has designed this system where you can send him graphics, and then he makes up from the graphics, he makes up an illuminated clear plastic sheet that you can change it color and make it blink or whatever. So the idea that I've got now with this telescope project is I've got 2 dishes separated on an east-west baseline. And if pulses are coming in from the sky and they're close together in frequency and they have a high enough SNR on both telescopes, then I record them. And actually, I record them even with just SNR, and then in post-processing, I look for close tones. And so it produces about 10 or 20 pulses every 3 seconds. So 3 seconds is the interval, and I look for 1/4 of a second for these pulses. And I measure the angle between the phase, the RF phase in the 3.7 hertz bandwidth on each one of the telescopes, and then I record them. I record that angle measurement, and then I can use that to measure the angle of another pulse that's very close in frequency to it. Now, so the idea is that if there's communication signals, then there shouldn't be tones close together. I mean, if there's noise, there shouldn't be tones close together. If somebody's communicating something and they intend to be discovered, then kind of like a PL tone in two-way radios, you want something that is recognizable against the noise. And so what I do in post-processing is to take anything with a 100 kilohertz separation and is present on both dishes above the 8.5 dB signal to noise ratio threshold. And I record that as a candidate pulse. And then I just scan this. I let the Earth rotate through to get the right ascension filter. And this is the system that I have on my farm here, that with the 2 dishes. So they're basically made up of petals, and I talked about this last summer at the conference, that I built this interferometer, and so this is the I'm increasing the size of the west antenna, so that's going out to 10 feet now, and it's worked out real well. It's dropped the noise quite a bit. There was a little bit of spillover. I used these sheets, these steel sheets on the east antenna and west antenna before to handle the spillover, but it works a lot better with a regular hardware cloth mesh going out to 10 feet on the offset fed paraboloid. So the feeds are it's offset fed paraboloid, so it has lower blockage. So this is just one chart from the paper, which is probably the most significant chart that shows the highest deviation from noise. So let me explain what this is. So out of the I don't know what the exact number is, but 10 pulses every 3 seconds for 61 days. All right, so this is 61 days of data, contiguous, 4 hours per day as the sky goes through the beam of the telescopes. This is the 1,280 candidate pulses that exceeded the 8.5 dB threshold and had signals closer than 100 kilohertz apart, and also had less than a 5-degree difference in the phase between the two tones. So if the two tones are coming in at the same time, and I measure the phase on one and I measure the phase on the other, and I get within 5 degrees of each other, then it's an indication that the other tone is probably, it may be related to the sky direction of the first tone. So the two tones are correlated in terms of having very close sky angle, only 5 degrees off. If the second tone, which is really close in frequency, was noisy, was due to noise, okay, random noise, and just happened to be that close, then it would tend to not have that phase correlation. So then what I did was I plotted here the number of pulses that are happening as a statistical measurement of the mean offset from the expected mean if they were random. So if you have like 1,280 pulses and they're just totally randomly occurring along right ascension, then you'd expect them to all have some average, which it turns out in this case is a binomial distribution. So we can calculate the mean, the number of expected pulses to have within each one of these right ascension bins should be 1,280 divided by the bins, although there's a triangular probability because of the fact that the right ascension and modified Julian date don't track exactly, and that's another slide to show that. But you'd expect that they would all look random in terms of where they're located in the sky. And it turns out that there are locations in the sky where there's a lot more pulses than I would expect to see. And weirdly, bin 52 is the second highest concentration of pulses along right ascension. Well, bin 52 is 5.25, centered at 5.25 hours right ascension. So it's pretty weird. It's got 2.5 standard deviations offset from the mean expected for that. So that's very significant, and there's lots more to do on this thing. So I've got a lot of work to do. So anyway, that's pretty much it. You know, that's the paper has a lot of plots about what frequencies these pulses were on and what modified Julian date occurred. How much was the actual frequency offsets? The frequency offsets for about 4 of the pulses that occurred in this direction were very low. They were down they were around 2.5 kilohertz. So they were unusually low. And it's kind of causing me to wonder what's causing the strange response at that direction in the sky. And so these are the 5 papers, and they're in these categories: electrical engineering and system science, signal processing, astrophysics, instrumentation measurement, and physics, popular physics. And turns out that I just happened to spot that this last paper just got chosen by one of the moderators to be put into popular physics. And there's only about 10 papers out of like 2,500 physics papers a month that get chosen to be put in popular physics. So, but hopefully I won't get a lot of calls from journalists and such, because I'm not making any claims about anything. So yeah, okay, thank you. Thanks. Yeah, if there's any questions or ideas about what's going on here, you know, I'm kind of I'm kind of befuddled. The fun thing about this project is that I have so many different ways to test alternative hypotheses, right? Like pulsars. Okay, so I can create simulated pulsars in software. I can make hardware pulsars. I can inject signals into the antennas and look and see what kinds of things occur with all of this. And another thing I want to point out is that the entire system is hardware based. There's a machine. This is all just one machine. So all the plots in my paper, I did not involve myself in like creating those plots. Okay, they were all generated in the softwares. So actually the software created this image, and I took the image right out of the software output and put it into the paper. So it's not like I'm analyzing these things, which is kind of neat because that means that I can take another 61 days and perhaps in a few hours, I can create a whole nother set of plots, that are just created by the system. And the system runs continuously. So it's been running all the time. And I just leave it running. So I've got a lot more data. There is a problem with RFI in that during those 61 days, I was really careful about the electronics that I used during those 8 hours. So I was trying to prevent any risk of cell phones, laptops, or whatever, and that was kind of a thing. So, but I haven't done that for the last 61 days. So if I do another one, I'm probably going to do another RFI quiet kind of time. Although I do have an algorithm that automatically puts our suspected RFI all gets put into another file. And then I measure the offset of signals from that to help weed it out. So anyway, yeah, so it's lots of fun.
All right. Thanks, Skip. That's really cool stuff. Anybody got any questions for Skip?
Yeah,
Yeah,
go ahead.
yeah. Great work. Very interesting, actually. Yeah, I was wondering about these pulses, actually, and why they seem to occur at certain right ascensions. And what I've noticed myself at the microwave bands, like up at like 12 gigahertz and stuff, there we have a lot of satellite interference, essentially. And what I notice is that like some spots where you point the telescope, the satellite interference is like way more often than other points. So I'm thinking like maybe these are like preferred orbits where the satellites are crossing through. I'm for example thinking like of these Starlink satellites that are like very clearly like you see them like coming one after another in like a shared sort of orbit. So maybe could something like this be going on, that like this is maybe just like from satellites just crossing through a certain part of the sky more often than another part?
It could be, and that's one of the problems with this particular location, which is I kind of have to live with it, is that it is within a few degrees of the geostationary arc. So there are a lot of satellites along there. They're, spaced a few degrees apart along the geostationary arc. And there's some that are defunct and they're pushed out to further orbits and all that. But so the beam width of the antennas I'm using now is about 8 degrees. So I am within the geostationary possibility. The thing is, the geostationary satellites move across the sky. So that's why I run these really long tests. Like in one of my papers, I think it was 100 and something days. So over that period of time, you'd expect the constellation to have moved away. And then I look for the distribution in days of anomalous pulses. So if they're happening in that direction in the sky, what day was it on? And I put those into my paper as well, and it's in this paper. So the idea is that, yeah, it's possible that RFI from multiple antenna or from multiple satellites looks similar, but then you run into the problem of how come it's only being recorded when it's, in that particular right ascension. Well, possibly it's because multiple satellites are moving through that area, and I'm seeing over a period of 61 days, I'm seeing interference from 5 or 6 different satellites. So that's, possible. But then the question is, well, why would the interference occur when the star Rigel is right behind the satellite? In other words, if another star was behind the satellite, which is offset in right ascension, how come it doesn't show up over there? Why doesn't it get distributed? What is the correlation between the location of the transmission and the fact that it's got the star Rigel behind it compared to where I'm located? You kind of follow what I'm saying? In other words, I agree completely. I mean, if I put satellite orbits into Stellarium, it just fills up, right? They're going over all the time. I think I've done that, or maybe it's in another app, but I see these satellites moving all the time. But the idea is, why should something transmit, extraneous pulses when the star Rigel it's near Rigel, it's not exactly there, but when the star Rigel is behind line of sight to me, to the satellite. And that, you could say, well, maybe there's something out there that's actually being placed at a fixed location celestially. But then the problem we run into is, over a period of 61 days or longer, in some of my papers, it would require thrust in order to stay there, right? Like someone would have to position an interfering source so that it's sitting in that place. And then why would they do that? Why would somebody, go to the trouble to do that? It's kind of it's a strange argument. But on the other hand, no, I mean, I'm not making any conclusions about what is causing any of these things. That's one of the possibilities.
Very intriguing stuff indeed.
Yeah.
Very
The
puzzling
thing is-
also.
Pardon me? Yeah. The other thing is, it's in the 1420 band, so it's in the protected band. Now, there's only part of the band is protected, so it's up to 1427. I go a little bit higher than that, but so there's, and I also in the paper I talk about which frequency it's on. It's generally not, it's distributed in frequency. It doesn't appear to be any specific location. And just a tidbit, I mean, an idea is that a wideband communication system, if someone wanted to convey a lot of information capacity, they would tend to distribute the transmissions over a very wide band of frequencies. So you might expect to see that. So, okay, yeah, thank you. Yeah, that's a good question.
Skip, you're saying those signals are 8 dB above the cold sky level?
So I calculate the signal to noise ratio in a 3.7 hertz bandwidth. And the noise level is calculated by looking at a 954 hertz bandwidth, 256 bins, and then measuring the noise in that bandwidth around the tone that's in that band. So in other words, that's the noise level. And the noise level is the system temperature, basically. The noise will be whatever the sky is looking at, whatever the telescope's looking at in the sky, but mostly receiver noise.
That would take a lot of transmission power.
Yeah, so the interesting thing about how big the transmitters have to be is I've done a lot of these calculations, and I've looked up what other people have written about it too, and it turns out it's not too impractical to build an interstellar communication system. In fact, I think one calculation I did said, okay, let's say they've got a Green Bank telescope, 100-meter telescope, and they've been able to measure our planet and determine chemically that there might be life there. And so they've put the thing, and I chose a 40 Erdani, and I said, all right, this is what is it? 18 light years away or something like 60. I can't remember the exact number, but in the tens of light years distant. And then said, okay, let's build a solar array the size of the Green Bank telescope and then convert that to an RF signal, transmit the signal in this direction, beaming it using the 100-meter antenna. What does it take on Earth to pick it up? And I calculate that within like 10 seconds of transmission, I can detect it with a 40-foot telescope at Green Bank. Okay, so it doesn't take a ridiculous amount of power to transmit light year distances, as long as the bandwidths are kept fairly low. So that's why SETI generally always looks in narrow bandwidths, you know, in my case, 3.7 hertz, because you can go a lot further that way. So, you know, I guess it's just a matter of calculating the numbers, and Project Cyclops report shows how it would work. The biggest issue is that I would think that it would have to be beamed. If somebody were transmitting omnidirectional, then it takes an enormous, I mean, that's a lot of power if it's omnidirectional. So it would have to be, I would think, initially someone who set up something that would beam the power at a likely civilization. And of course, you know, if they've got a big antenna, they can also listen, and they can find out that we've transmitted some things if they're close enough, you know, from the time we started transmitting.
Okay, Ed, did you have a question too? No? Okay.
No.
All right. Well,
Thank
thanks,
you.
Skip.
Thank you.
Really good stuff.
Okay, thank you very much. Let's
Okay.
see. My mouse is stopped working. So can you stop sharing me?
I will.
For some reason, I don't. I think I can see it just barely. Where is my mouse?
All right, I got you. Okay.
Thank you.
All right. Thanks, Skip.
Thank you.
All right. Well, let's get Dimitri, because he's in our time zone, different time zone here.
Hi to all. I'm very glad to see you all again, and my greetings to all. Here is not too good internet. I thought, I think I thought some to tell some words about papers. My papers published in April issue of the journal. If here internet is not too good, and maybe some delays in translations, just 5-10 minutes about this paper. Just a moment.
You're muted, Rich.
Dimitri, were you going to try to present something now? Is that what you? No?
Maybe present now. Just a moment. I'm.
If you want.
I want to find how to share it, but it's not. I can find how to share my screen. Just a moment.
Bottom left on Zoom, or bottom should be like a green arrow pointing up is the share. Yeah, you getting it? You see
It's
it?
okay?
Yeah, it looks good.
Okay. Uh, just a few words. I think it needs some comments. This work. I mm, I was building my receiver since 2018. Um, much of works was done. So, this paper is the result of this work. Uh, 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 this work is about small single dish antennas and telescopes. It characterized by high system temperature and low forward gain. Uh, mm, it leads to rather high system equivalent flux density (SEFD) and uh, it needs much effort to pick out mother line from noises associated with very long integration time, several hours and maybe multi-day, several day observations. Uh, mm, some investigation was made how to pick out mother lines and what mother lines can I pick up from the noise with this very limited sensitivity of small dishes. So mm, uh, maybe radiometer equations for mother spectral lines. I didn't find these equations exactly in literature. Maybe exists so, but I I was needed to believe it by my own means. Uh, mm, this is mm, used. This is derived from standard, very well known radiometer equations, uh, mm, and use SEFD instead of um, system temperature in numerator, uh, and some coefficients reflects background noise peak factors is taken about 3 for Gaussian noise and uh, as bandwidth we uh, is used at resolution bandwidth uh, mm, as frequency band in denominator. Um, Resolution bandwidth is defined defined by mother line wise. We need uh, to observe and usually choosing about 5 times lower than expected line wise of the measure. So these equations describe situations when mother line peaks it's about the same level with background noise peaks and in longer integration time, should lead to the mother peaks goes over the noisy peaks. So you can see the details in the April's paper. Next the receiver systems block diagrams consist of hardware parts and software parts. Mainly uses SDRs in hardware. The radiometer equations may define the needed integration time to pick out measure lines from the noise. So to pick out, we need rather long averaging. This is shown in one of software block. Feedback in averaging is it means that averaging is is realized by on-fly process without storing any intermediate dates in computer. Needed averaging time, needed number of averages is defined by resolution bandwidth and needed integration time. This is a very simple formula. Next, I would say some words about for following post-processing of receiving the spectrum of receiving of receiving already average spectrum. Long averaging is usually shows very on flat, uneven frequency response of receiver. This is example of my USRP receiver, very unflat frequency response characteristic, and it should be correct. It need to be corrected, have to be corrected. So for corrections, it is needed to collect background spectrums when antenna is slightly moving out of source of the measure. Background spectrum and mother collective spectrum should be as close as possible. So the difference in noise in mother spectrum and the background spectrum should be as minimal as possible. This is formula for correction for background corrections, and corrected spectrum, normalize it to unity and shift it to 0. can be used immediately to get the spectrum in flux units in Yansky. Background corrections bring some noise to resulting spectrum. So background collecting background should be as long as possible, but not too long to keep to keep the background in mother spectrum, background noise in mother spectrum, and background for corrections should be not too different. As you can see, the difference leads to some deviations in correct spectrum, some deviations from zero. This demonstrates the difference between background and background collected for corrections and background in mother spectrum. You see lines of metre. You see lines of metre. The data was collected in last September. CFUS A for 6.7 gigahertz line. Integration time for measure spectrum about 1.5 hours, and background is averaged 3 hours. Longer variations, longer average leads to more difference in backgrounds, and it needs some corrections. The slant slanted plots to make it more straight around zero. And what I have to say that that system temperature and SERD should have to include because background spectrum for background corrections is collected immediately when antenna is shifted, is light shifting from measure. It system temperature and CFD contains the atmospheric noise and other noise like galaxy noise, and it should be taken into account. This is most significant for millimeter wave bands for 22 gigahertz measures, and I hope some I hope the line is for methanol and chromium oxide and 44 gigahertz also can be observed by meter means. I am now working about 43, 44 gigahertz receiver. I don't I don't I don't promise it will be ready in the near future, but I hope at least um, I'm planning it about half of 1 year to it will be finished. That's all for now. If some questions, I'm glad to reply.
Good stuff, Dimitri. Anybody got any questions? It looks like this is a great way to get their good design with the equations.
I
Anybody
have
else?
a couple of questions quickly. The sample rate that you're actually running and the number of bits in the A to D that you have in your system, what would that be right there?
Sample rate mm, is defined by full receiver bandwidth. Uh, with the receiver bandwidth will have to be should have to be as wide as so all major spectrum should be have to be uh, mm, uh, receiver bandwidth have to be mm, more large than expected measure spectrum with all features with all lines for 6.7 gigahertz. The bandwidth and sample rate can be 1 megahertz on 2 megahertz. It's more than enough. For 22 gigahertz, it have to be 4 megahertz. And I and I and I can't imagine how wide it will be for 44 gigahertz and 10 megahertz. It's it's very wide. Number of beans designated by number n, and it's have to be defined uh, have to be defined by resolution bandwidth. So sample rate divided by number of
Okay.
Sample rate divided by resolution bandwidth give n number of beans, number of fast Fourier transform points. It's and when resolution bandwidth and resolution bandwidth should be as low as to track the shape of mother lines, and should be rather low, and it makes number of beans number of beans larger. It's okay.
Okay, I understand.
Thanks, Dimitri. Let's go to Edward.
Yeah,
Now,
hi.
please again.
Sorry?
Go ahead, Edward. Let's see. I'll try to get him. Edward, you there?
Yeah, yes, sure.
There you
Yeah,
go.
I just thought that maybe Dimitri wanted to say something, but apparently not. Okay. Yeah.
Okay.
Yeah, I have a couple things to share today. Namely one failed project and one that was successful, which I've been working on for quite a while. Can I go ahead and share?
Go ahead.
All right, there we go. Yeah, can you see?
Yep.
All right. So yeah, yeah, I don't have really all that much in the way of new observations, but I do have a little success in that I have now completed about 2 years of water measure observations of the source Westerhout 49. So I've been trying to observe this source every month to track the changes in the spectrum. Well, for the past year or so, it became more like once every 1.5 or once every 2 months, but I'm still regularly doing or semi-regularly doing observations of this interesting source. And the failed project is the telescope mount, unfortunately. That's not going so well. So just to start off with that, so currently I'm placing my 1 meter dish on a HEQ5 equatorial mount, which I originally bought for astrophotography, which is my other hobby. And this works fine. The mount is sturdy enough that it can handle the 9 kilograms or so of the dish and all the equipment around it. But it's not ideal. Like it's kind of clunky. I have to bring it outside for every observation session and bring it back in again because it's not weatherproof and everything. So yeah, I wanted to have a separate mount for this that I could just like ideally just leave outside for weeks or months for longer observation projects. So yeah, this new mount should of course be able to handle a 1 meter dish or maybe even a little bit more weight. If I ever want a slightly larger dish to play with. And also it's needed to be able to track and point quite accurately because at 22 gigahertz, the beam width of this 1 meter dish is only 1 degree. So you're talking about like at least a 1/4 of a degree accuracy if you really want proper pointing and tracking. And then the final requirement was to keep the cost a little bit down because if you're going to look out for rotators that are capable of like sub-degree accuracy tracking, then yeah, these are going to cost a couple €1,000. And I really wanted to try to make something for a bit less cost than that. So in terms of the control software, so I ideally wanted to have like a motorized mount so I can just like point it and do automatic tracking and observations. I could have gone, of course, for just a simple stationary mount, just doing drift scans. But the problem is at 22 gigahertz with such a narrow bandwidth of only 1 degree, or such a narrow beam width, I should say, sorry, not bandwidth, beam width, of course. That's only like every transit is only going to take like a couple minutes. So if you want to collect like an hour of data for your project, then it's going to take weeks. It's very slow. So that's not ideal. So yeah, tracking is really a must at these frequencies. So yeah, in terms of the control boards and software for pointing and tracking, I know a lot of amateurs are making such things themselves, and I was like, this should be a solved problem by now. So I started looking around, and eventually I found OnStep, which is like this open source telescope control project. And there's a lot of people who are tinkering with this in the amateur telescope making community and amateur astronomy community. And there are even some people who are like making and selling just readily available boards for this. So that's kind of nice, saves a lot of effort and time in theory. And another nice feature of OnStep that it's possible to control the mount via a planetarium program like Stellarium or K-Star. Not strictly necessary, of course, for radio telescope, but it's just a nice extra. So in terms of the hardware, so I opted to go for a altazimuth mount, which is a bit easier to build for these types of telescopes, for these types of dishes. I noticed that I did make some designs for an equatorial mount, but you very soon run into a problem with like the dish bumping into the mount somehow at some point. It's also an issue with the current mount that I'm using. I have to be a little bit careful that it's not gonna bump into the mount at some point. So the design of this mount was kind of inspired by some examples that I found that were being built by amateurs who were posting about it on like the Cloudy Nights Astronomy Forum, and also in the OnStep showcase. There are some projects of people like building like these big altazimuth mounts for their Dobsonian telescopes. And the interesting thing is that they generally used the sort of like large belt and pulley systems, like toothed belts, for the to drive these mounts. And they were essentially like 3D printing these very large pulleys that could be like tens of centimeters across. And I found this quite an interesting technique, and I wanted to try to make something more similar, because I was thinking like, if these types of mounts are able to like handle and accurately point a very heavy Dobsonian telescope, they should also, something like this should also be able to like point a 1 meter dish, no problem. So yeah, I went for a both axes of my mount are have their own stepper motor, and then there is a 100 planetary gearbox, so 100 reduction, and then for the azimuth axis I have then a 1-to-8 belt and pulley system, and for the altitude axis it's a 1-and-4 reduction. So you end up with 1-and-800 reduction on the azimuth axis and then 1-and-400 reduction on the altitude axis. So these numbers might seem high, but they are fairly normal for amateur telescope building. So I've seen plenty of examples of people using like anything between like 1-in-500 to 1-in-1500 reduction. Oh yeah, and the total cost of all the hardware, all the nuts and bolts and metal and belts and pulleys was around 600 euros. So then came the first big challenge. It was actually making these large pulleys. So the azimuth pulley was, for example, 32 centimeters across, which is very large, and you can't really get these pulleys, at least not for any reasonable price. I was also considering going for warm drive, but high quality warm drives are also very expensive. So yeah, then I was looking into, can I 3D print these pulleys, because there were plenty of examples of amateur astronomers 3D printing their pulleys for their telescope mounts. Unfortunately, I don't have a 3D printer and I don't have any experience at 3D printing. So yeah, this was kind of tricky. So yeah, my dad and I ended up asking around in our circle of friends and colleagues if anyone has any idea how to do this or if they could help. So there was one colleague of my dad who had actually some experience with 3D printing, and he was actually printing some pulleys for some projects, but he said it was very, very difficult. And this is because if you 3D print a pulley or anything really, the plastic of that is being 3D printed, it contracts a little bit. So you end up with like a slightly smaller diameter of the pulley than it should be, so the pitch is not right. and the belt won't fit around neatly. So he needed to like adjust the size of his design ever so slightly, and then print it again and test it and do this again and again, like 4 or 5 times until he had the right size. And he wasn't very enthusiastic about printing these big pulleys for us. So we had to think something else for ourselves. So my dad came up with this neat little machine that you can see in the middle. So this is a XY table, and mounted on it on a 90-degree angle is a rotation table with a worm gear. And this way we are able to like turn our pulley by a set interval of degrees. I believe it was something like 3.6 degrees for a 100 feet pulley. And then we could cut a groove and then repeat this until we had like cut the whole pulley, and then we could just like trim the size until the belt fit around neatly. And this actually eventually worked really well. So I was really happy with how this part of the project turned out. What I wasn't happy about was the control board and the software. So I ordered a mini ESP3 board. These boards are being made by George Cushing, who is one of the contributors to the OnStep project. So the first thing I needed to do is to edit the configuration for my particular setup. So yeah, configuration contains all the relevant parameters, such as the number of steps per degree that the stepper motors need to make, or the type of stepper drivers that you use, that kind of stuff. I'm not really going into much detail. If you're interested in this kind of stuff, there is plenty of documentation on this available on the OnStep wiki. Then, of course, I needed to flash OnStep on the ESP32 microcontroller, which I also succeeded in after some initial troubles. I had no prior experience with microcontrollers before, so this was really quite a achievement for me personally, at least. And then came the testing for tracking and pointing, and yeah, this was really not a success. So George suggested to me to turn on auto start tracking in the config.h file. So that means that the mount should start automatically tracking once the board is powered on. So if you hook up your motors, you should see them start slowly turning. And yeah, whatever we did, it just didn't work. So yeah, still after 2 months already, I still have not got this to work. And yeah, at the moment, I'm really rethinking, like, should I really continue going this way, or should I just abandon my attempts at integrating OnStep into my project and just go with another option, or just like, you know, keep it as a stationary mount and just do the drift scans. Okay, so yeah, that was the failed part. Now for the successful ones, that are the major observations. So yeah, these are all the spectra that I collected from Westerhout 49 in the past 2 years. So on the left side, you can see sort of waterfall plot, and on the right-hand side, it's the same data, but just plotted like as the individual spectra. So this source is in the star forming region. So there's like lots of star forming going on. There are protostars, there are shock waves, there's molecular outflows. There's like a whole lot of stuff going on. And you can see that the spectrum is very complex. So there's like plenty of peaks. There's lots of red shifts and blue shifts. So just a note on this, we are actually only looking like at the central part of the spectrum. Because there's like red shifted and blue shifted peaks all the way up to like minus and plus 300 kilometers per second. So like even with like the 6 megahertz of bandwidth that I currently have, I'm like only like covering like the central portion of this spectrum. But we can already see like a lot of interesting stuff happening. So mainly so-called flare events. So this is when a feature or a peak in the maser spectrum suddenly becomes like way brighter and then fades out over a period of a few weeks or months. And yeah, I have numbered like 5 of the most prominent flares that occurred. There are also some smaller blips occurring here and there. And what is interesting is that 3 of those, so the flares that are number 3, 4, and 5, all seem to occur like in this very close in the same velocity range, so somewhere between -5 and -15 kilometers per second, and also very close together in time. So I was wondering, could these events be related to one another? So yeah, to really understand this, I just want to give a very brief recap, if I have the time for it, of how masers work and how these flares could arise. So essentially, like a maser is the microwave equivalent of a laser. So just like how a laser amplifies light at a very specific wavelength, a maser does the same, but for microwaves. And this occurs through a process known as stimulated emission. So in stimulated emission, you have a particle like an atom or a molecule, and you essentially kick it to a higher energy level, and it stays there for a while. And when a photon comes along, which has exactly the right energy, it can trigger this atom or molecule to fall back into a lower energy, emitting an extra photon in the process. So from 1 photon, you get 2. But of course, you need to put energy into this. So you first need to bring this particle to a higher energy level, which is known as pumping. So essentially, in order to get to produce a flare, so a sudden increase in the brightness of a maser, there's essentially 3 ways to do with it. So first is an increase in the pumping rate. So simply like putting way more energy into the system. Because if there's a higher pumping rate, then there's a higher chance of these like stimulated emission events occurring along the line of sight. So you see an increase in the brightness. There's more amplification going on. The second way to do this, and this only works if the maser is unsaturated, so if the pumping rate is higher than the stimulated emission rate, is to increase the number of seed photons. So essentially the number of photons that trigger the stimulated emission. And the third way, finally, to increase the maser brightness is to increase the amplification path length. And so this is essentially the masers that we find in outer space. They are essentially in very, very low density gas. So you need a very long path length of like thousands or even millions of kilometers to get a significant amplification. So if we look at the environment of these masers in star-forming regions, as I said, it's very chaotic, but the general picture is that they often occur in some sort of outflow. So you have a protostar in the middle, so big ball of gas that's collapsing to form a star. And there's some gas also like flowing away from this protostar at speeds of like, at velocities of like tens or hundreds of kilometers per second. And there are shock waves passing also through this gas. And these are actually exciting these masers. They are pumping them. So we see these masers like sort of tracing like tiny little arcs, apparently like along these shock waves. And they only occur like in like very small so-called maser spots where the conditions are just right. So yeah, to cause a flare event in such an environment, we can look at 3 different sort of scenarios. So the first is an accretion burst. So like a whole bunch of gas just is gobbled up by this protostar and essentially like causes like a burst or like an eruption of heat and infrared radiation, which can then like cause more pumping of the surrounding masers and cause them to be like way brighter than normal. Another possibility is that there's a shock wave passing through this maser medium, through this gas, which is triggering increased pumping and causing these masers to become brighter. And finally, there could just be a chance overlap between different maser spots. So essentially, if you have like a maser spot along the line of sight overlapping a maser spot that's farther away, then the foreground maser spot can essentially amplify the microwaves that are coming out of the background spot. So yeah, when we look at some of the individual flares and also some of the smaller events, they also seem, most of them seem to occur like in just like one single feature, one single frequency. So these could be explained just by a simple chance overlap. So yeah, in this scenario, as I told you, you have a foreground cloud moving along in front of a background cloud, and essentially like amplifying the radiation of the background cloud. So you sort of get a very strong beaming effect. And this only works if both clouds are moving at the same radial velocity with respect to the observer. If they're moving at different velocities, then from the perspective of the foreground cloud, the radiation from the background cloud will be red or blue shifted, so it won't be amplified effectively. So that also explains why you only see like amplification at one very specific frequency, one specific major feature. But the apparent multiple flare at these velocities of -5 to -15 kilometers per second is a little bit more mysterious, because it's a lot harder to explain by just a chance overlap. Because then there need to be like multiple clouds at once, like moving at multiple velocities to achieve this. So perhaps there's like something else going on, maybe like an accretion event that's like triggering a whole bunch of masers in the region, or maybe a shock wave passing through these maser clouds and lighting up these masers like consecutively. We don't know, but at least like it's interesting to speculate about these things and think a little bit about the actual astrophysics behind our observations. Okay, well, that was it. Are there any questions?
Eduard, questions is maybe you can share some photos and drafts about HEQ5 mount and how the dish is mounted mounted on the high AQ5. I see some your photos. Maybe you can share photos and drafts. Oh, thanks.
Yes, sure. I'll have a look if I can find any pictures. If I can't find them in this session, I'll just put them in a post on the Sarah forum.
I'll comment also that there is a workshop in the BAA astronomy group. I posted in the notes there that covers Python, and it's a 4-session workshop, and it's very good if you haven't got a lot of experience programming. It's a good way to learn something about Python. And in that workshop, he talks about controlling a motor. And this might be a motor that you would use for antenna control for Hazel. And it explains how to do that using a PicoPi. And so there could be a learning case that you could learn Python and get your motor control system working properly.
Okay, thank you. That's interesting. Well, actually, I do a lot of programming in Python, so at least that's something I'm a bit familiar with. So that would be interesting to look into. Thank you very much.
Mm-hmm.
Any other questions?
Edward, was that a brass gear that you cut?
No, it's not brass. I forgot to tell the material, but it's actually this Trespa. This is very hard plastic, actually. A lot easier to cut than brass, and a lot cheaper also.
Edward, what problem did you have that that the on-step electronics won't drive the motor that you have, or what's the nature of the problem?
Oh man,
I've been thinking about those cards too, but I haven't bought one. I just wondered what trouble you were having.
Well, I wish I knew. That's the problem.
Oh.
I'm really not into electronics. My dad has studied electronics, but he doesn't know much about microcontrollers at all. So we are both like extremely puzzled about what's going on and why we just don't seem to get it to work. So initially we thought that maybe the microcontroller is just somehow broken or something is wrong with it, because it didn't seem to give like any output to the to the stepper drivers. But that was
Well,
very strange. So
stepper driving usually requires a separate power supply, of course, for the motor,
yeah,
and probably some series resistances. Their stepper motors are kind of funky creatures to drive, so that may be the problem. Interfacing to the stepper motor. Okay,
yeah.
I just wondered if you had a specific problem that you ran into.
Yeah, well, the problem doesn't get more specific than like we just seem to can't get it to
No.
work.
True, that's true. Yes, that's quite true.
Quite frustrating, actually.
Gee whiz. Well, that's good to know. I wonder. Okay, thank you.
All right. Any more questions for Edward? All right. Great work. Good stuff. Thanks for the maser overview. That was really good. Alex.
Hey, good afternoon. I just have a few slides, and a couple of them might be of interest to Edward Hartman. Let's see. Share screen. Share. This is a composite of all of the antennas that I have built over the past several years, and not in the order of their construction, but what I wanted to show you was, well, recently someone was asking if they could see any hydrogen line spectrum out their window of their second-story apartment, and I questioned that, and I suggested they build just one of these simple cylindrical tuned waveguide antennas to see if they could see anything with this before they progress on. And so all of these are in my collection, and I have captured data from the same part of the sky, the bright Cygnus area. And this was the unmodified scope in a box, and through a few years of add-ons, I have wound up with this, and it's a 0.27 F to D ratio, a Tom Henderson LNA, and I spent a lot of time refining this. But there are some steps along the way. This is the umbrella antenna that I built, and these are a couple. This is a 3/4 and a 1.5 meter long disc Yagi, and this is how they compare. And I thought this was fairly interesting, and it's pretty close to correct values. And what you might want to see here, Ed, is this is about all I got, which is about 0.75 dB above cold sky with the unmodified scope in a box. And my little umbrella antenna came out about 1.25. And then the two disc Yagis, I was impressed with this with the 3/4, and especially this, considering its narrow footprint to the sky is only looking at about 6 inches in diameter, that it's the amount of energy that it captured is so much less than this now 1.2 meter diameter parabolic reflector. These have some interesting properties I'm going to show you in the next slide, but this is to give you an idea of what you can do. You can take this an unmodified scope in a box, add some side panels on to reduce the spillover. Actually, it's the reception of ground noise, and dramatically increase the performance of your basic 1 meter Wi-Fi dish. And I've spent a lot of time over the past 3 or 4 months working with these disc Yagis. They're circular patch fed, and this is what kind of has been and new to me, and I've not seen this shown anywhere. I've not found any information about this, but the reflector to feed is very critical. It has 10 millimeter spacing. You go down to 9.5 or 10.5, it shifts the frequency significantly. And also the distance between the feed and the first director will adjust the frequency. But also 1.5 meters away from that, the whole system is much more of a resonant structure than I would have expected. I would have thought by the time you got this far away, the disc spacings here would have had, fairly minimal effect on the system's performance, and it's not true at all. This was an experiment to say, how well can I tune this thing? And 5 millimeter shifts in this spacing allowed me to tune this to like almost perfect 50 ohms and very little complex impedance, to where I got a return loss of almost 50 dB. And it was because of setting this up for 1.42 to the right frequency, and then up here adjusting this to remove the complexity of the impedance. And this to me is quite fascinating. So that's the story. Any questions? In fact, does anyone have any better information of how a Yagi works?
All right.
Okay.
Thanks, Alex.
Yep.
Don.
Almost got me napping. I really have nothing to do at this time. I finally finished I had to build a little simulator to simulate the movement of my big dish, so that I can diddle with the drive without crashing something into a pile of metal. So that's finished, and the drive system is undergo.
Okay, thanks. Bob.
Yeah, I'm working on I have about a 1 meter dish with a controller on it, and I'm trying to get that working. I'm having to rebuild some of the electronics in it because I didn't get all the information to start with. I'm going to make my own drive system. But what they did in the commercial version was, I was going to mention this, a couple of you have mentioned running your dish into the edge or too far. They put micro switches, which are just a little switch with a lever on them, on the extremes for the cam, so that when the dish gets to that point, the micro switch opens and the motor can't get power anymore. So then you can let your controller work, and if it goes astray and gets over to the micro switch, then it's your safety, your backup.
You can make a diode array so that it will enable the motor to drive in the other direction, even though it stops it in the direction of damage. It'll stop the motor in that direction, but allow you to drive it actively in the other direction without any problem. It's just a simple diode array that uses the micro switch to switch the direction of motion. It's available. Let's see, Paul Wade, I think it's Paul Wade made some of these, and you can actually just take some diodes for yourself and figure it out. It's not that difficult to do.
Right. Yeah. Usually you're reversing the DC power on the motor, and so using the diode.
Exactly. Yeah, that's exactly it. And it'll allow you to drive it away from the stop.
Right. And so I've got that going myself, and then also I've got some of the 6 gig transmitters because I'm interested in this Maser stuff. I've been kind of boiling along on it for a while in the background, but I've got the transmitters and I've tried to do some characterization on them, and I can see they're going to work well if I can get there. The tricky part is getting a real good stable LO to keep them at the right frequency, which I'll probably end up using a Leo Bodnar Mini for that. But hopefully one day I'll be able to collect some data like folks have shown today. I find that interesting. Anyway, that's all from me right now. Rich, back to you.
Telling me
All right, thanks.
there's some very reasonable doublers available on eBay. Very reasonable frequency doublers on eBay. 6 is hard to reach with some of this stuff, but 3 is relatively easy.
Yes,
And
I'll purchase some mini circuit stuff to get me up to the raw frequency. But I'd be interested in seeing what if you post a link in the notes about these doublers that you're referring to on eBay, those would be interesting to see.
I could do. Yeah, I suppose I could do it at our next meeting or some such.
That'd be fine.
Okay.
Thank you.
Sure.
Okay. MFB. I don't know who that is, but must be just listening. Joseph Sandy, I think you're last.
Am I? I don't actually have much for today. I'm also just here to listen and learn new stuff.
All right. Well, glad to have you.
Thank you.
Okay. Any last words for anybody? All right. Great RTOP today, and see you in 2 weeks for the Drake's Lounge. See you, Bray.